Okay, hi Year 11s. If I sound a little bit exasperated, it is because I actually recorded this entire video, but it turned out for some reason the screen where I was doing all the writing was completely zoomed in, so you couldn't actually see most of it. So I'm doing it from scratch again. Now, hopefully it'll be a little bit quicker. It was about 15 minutes last time, so let's see how we go. Now, this section, what I'm doing is I'm going to explain a bit of it to you, just like I would try and do in the classroom. Obviously, you can't ask me questions in real time, but hopefully, the combination of me speaking as well as having a look later at the textbook section to see it explained in a different way. Hopefully, that will answer all your questions. Worst case, you send me a message on Daymap. I'll see what I can do. Don't send it or don't bother sending it to me on Thursday because I'm going to be in surgery. But send me something on Friday while I'm sitting there with my feet up. I'll probably reply. Now, dilution is, as you probably already know, colloquially, we're taking something that's got more concentrated and we're diluting it. We're adding, let's say, if it's a solution made of water, we're adding more water to it to dilute it. Now, the most important concept that you need to know when we're talking about dilution is you need to know that when you dilute something, you're adding the solution or the solvent, but you are not changing the number of moles of your solute. The stuff you're dissolving, the stuff that that you're measuring the concentration of, the amount of it doesn't change. So the amount of it, as you know, actually no, we'll go back to here. So we know the concentration equals N over V, the number of moles over the volume. If we rearrange that, we get this equation here, which is N equals C times V. Now, the number of moles is equal to the concentration of our solution times by the volume of our solution. If we have more of our solution, we obviously have a larger number of moles of it. Now, this is a constant when we do dilutions. So what that means is that if we have a solution, let's say we have a concentration of our solution before we dilute it, so we call that initial, and we multiply that by our volume of our initial. So we have our initial concentration and however much of it we have, that will give us our number of moles, and that will be equal to the concentration of our final solution after dilution multiplied by our volume of our final solution. Now, this expression here is important. It gets used a lot. So CI, sometimes you can see it as CI times VI equals CF times VF, just, to save some time, having to write final and initial over and over again. So yeah, you'll see this expression. You'll use this a bunch. So it's important to remember. C times V initial and C times V final will be equal to each other. Now, before we go further into this, I need to introduce a concept called standard solution. So we have our standard solution. Now, let's see if I can write it properly. Now we have standard solutions. Now, a standard solution is a solution of whatever compound, whatever substance that you're interested in, but it has an accurately made or accurately known concentration. Now, the way you know the concentration is because you know what the substance is, you've measured the right amount of it from using a scale, you've put it into a flask, and you've put an accurate amount of liquid in there so that you have overall known concentration. Now, I'm just going to choose something common, let's say like sodium chloride. So if we're going to do an example with NaCl, so a solution of sodium chloride, we can make any concentration we want. Obviously, there's a limit based on how much will dissolve, but let's say we do a concentration of our initial concentration of our standard solution. That means the substance, the solution that we're going to be using in an experiment, for example, will be, let's say, 2.0 moles per liter. Now, just as an aside, you might see this referred to as 2.0 molar, capital M. That capital M is not molar mass; it's a unit molar. Just like N over here. That N is a variable. The unit for that is moles. Over here, this is over this here is a unit called molar, not the molar mass variable, not the m, like the whatever grams per mole. Either way, so that's our concentration. If we want to make that concentration, we will need to add a certain amount of our sodium chloride if we want to make up a 2.0 molar solution. It'll obviously depend on how much we make. So if we use this apparatus over here, so this is a 500 ml volumetric flask, our volume is going to be, actually, for this standard solution calculation, this CI and V are not super relevant. So just for this calculation, we're going to do C and V. So C is 2.0. Our volume is going to be 0.500 liters. Now, that is our 500 mils, but in liters. Now, you're always going to have to convert these to liters for our concentration. If we're using a concentration of moles per liter, you'll be using our volume in liters. So we can work out N, which is C times V. So C times V is 2.0 moles per liter times by 0.500 liters will give us 1.0 moles. Now, I've got two significant figures here, which matches the 2.0, which is two significant figures for our concentration. Our volume has 3, but our concentration has 2, so that's going to be limiting it. Now, we know the number of moles of sodium chloride, but if you put some sodium chloride onto a scale, you are not going to be getting a number out in moles. So we are going to have to find out the actual mass of this stuff that we're going to be that we would need to use. So using this equation up here, which you are well and truly familiar with, to find out our mass, it'll be number of moles times by our molar mass. So again, the unit molar and this capital M are different things. If we have 1.0 moles of our substance and our molar mass of sodium chloride, which I've looked up, is 58.44 grams per mole, that will give us 58.44 grams. Now, again, the limiting, so the number of moles, the calculation is limiting, but I'm just going to write our full 58.44 grams anyway. So if I have 58.44 grams of sodium chloride and I put it into a 500 ml volumetric flask and I then fill it up to 500 mils with water, the concentration of that solution will be 2.0 molar, so 2.0 moles per liter. Now that you know the process of making a standard solution, there are some extra details, but you can see them in the textbook. I'm going to try and make a new solution from this one. So I'm going to take some of it and I'm going to dilute it. Now, yes, the number of moles in this whole thing is 1 mole. But if I take some of it, not all of it, the number of moles is going to be different. And it's going to depend how much of it I take. So what we're going to say is I want to make a new solution. And I'm going to have a new concentration. So our final concentration is going to be 0.25 moles per liter. So instead of 2.0, it's going to be 0.25. So it does matter how much of it I make. So let's say for an experiment, I want 50 mils of it. So my final volume is going to be 50 mils, which is 0.050. Let's say 50, yeah, we'll just go two significant figures. 0.050 liters. Now, we do know something else, and that is the concentration of our standard solution. So that will be our initial concentration. And that is going to be, oh, can't spell initial properly, but anyway, that will be 2.0 moles per liter. So we know the concentration we want to have. We know how much of it we want to have. We know the concentration of our starting stuff. I need to know how much of this standard solution will I need to then dilute up to 50 mils to make my final concentration of 0.25 moles per liter. We can take this, this equation here and we can rearrange it to get our volume of our initial standard solution. So V initial is what we're looking for, and that is equal to CF times VF divided by CI. Now, our concentration final is 0.25 molar, so moles per liter. Multiply that by our final volume, which is 0.050 liters. And we divide that by our concentration initial, which is 2.0 molar, which will give us our final volume. Obviously the molar and the molar will cancel out, leaving us with our volume in liters. That's what we expect. Now, I could probably do this without a calculator, but I'm not going to bother because it'll take me time and I'll probably make a mistake. So 0.25 times 0.05 and then divide that by 2. And that gives us a value of 0.0062. Oops, that looks like 0.00625 liters, which is equal to 6.25 times 10 to the negative 3 liters, which is equal to 6.25 milliliters. So you need 6.25 milliliters of it. If I'm going to do it in the correct number of significant figures, it would probably be 6.3 milliliters of our standard solution. Yeah, just double checking if it's correct. Yep, cool. So I had to dilute that 8 times. So that's about right. So I've got 6.25 milliliters roughly of my standard solution. If I put that into my 50 ml flask, I add in enough water to bring it up to 50 mils, I will have diluted it, and the concentration will now be 1/8, so 0.25 instead of 2.0. So this is the process, of one of the processes of, calculating one of these 4 variables. So one of these 4 values. Each question, will be written in a specific way to give you certain information, and you'll need to, find one of the 4 pieces. So you'll have to be able to rearrange this in a couple, a few different ways to be able to work out the answers. Now, just quickly double checking. Just want to have a look at the questions. So after you've listened to me, hopefully you understand what I've done. You'll need to go and look at the information in the textbook, read it in their way of explaining it to see if it helps make things more clear. If mine isn't particularly clear for you, then you'll be doing the questions. I just want to quickly double check that the questions, I've given enough information for you to answer it. First one, you got students preparing a 500 ml standard solution from different stock solutions. So they're trying to say that we take a concentrated substance and we're going to make different standards. You're always going to be taking something more concentrated and making something less concentrated. If you have a low concentration substance, you'll need a lot of it. If you have a really high concentrated starting solution, you'll need less of it to make a particular concentration. Otherwise, I think I've given you enough information here. Yep, it's looking pretty good. So now, just before I finish, if you get up question 24 and 25 done, I recommend having a look at the next section, which is stoichiometric calculations for precipitation reactions. We've done a bit of this stuff before. It's just covering our bases, just to make sure you really understand this stuff. It's only a couple of paragraphs of information and 3 more questions, 26, 27, 28, and 29, actually 4 more questions, which I would like you to try and get done before I see you again next week. So giving you a bit of homework to make up for the fact that a lot of you probably didn't do any over the holidays, but either way. So I hope that's helped, and good luck.